Morning, guys. So today the lesson of the day is the original t-test. I'm not going to spend a lot of time on this. Very much like your textbook, Sokol and Rolf's Biometry. I think you'll find there that they basically say, look, you can do this with an ANOVA. There's really no reason to have a t-test anymore, except that it's talked about a lot. You'll see people doing it, and so it's important to recognize what it does. But computationally, it gives you exactly the same p-value if you were to do a one-way ANOVA with two groups as when you do a t-test. And so there's really no advantage or disadvantage, except that ANOVA is a broader kind of analysis that can do many kinds of experimental designs, whereas a t-test is rather specialized and rather focused. Now, we've already talked about one kind of t-test, and I mentioned that that we, in a previous lesson, we have t equals yi bar minus mu over SE, and where we're testing whether a particular mean could have been drawn from a parametric population with a mean mu, and what is the probability of that. And we said it was just that this ratio, really, is what it is distributed as t. And so t can take on a value between 0 up to some fairly high values, 10, 20, etc. Okay, so, and the higher the value, the more likely it is that we can reject the null hypothesis. More likely we'll be correct in doing so, or we won't be incorrect in rejecting it. Okay, so we get a p-value associated with a t-value, and we've already used that test to do that kind of thing. And in fact, that's something you might use a t-test for. I've used it for in various publications. But the traditional t-test, I'm using less and less, and using just an ANOVA. But let's go ahead and write out the t formula. So this is again from your book, y1 bar minus y2 bar. It's a little bit more complicated formula, mu1 minus mu2 in the numerator, all divided by this humongous thing in the denominator, the square root of everything here. We'll put in brackets n1 minus 1 times the variance of n1, sample variance, plus n2 minus 1 times the sample variance of sample 2, all divided by n1 plus n2 minus 2. We take this entire quantity, oops, I'm sorry, I should have put a bracket there, and we multiply that by n1 plus n2, all divided by n1 and 2. So this looks like a humongous mouthful, but in fact it's actually not all that different from this if you compare it. Instead of having this simple standard error here, which is, remember, the standard deviation of the mean, the sample means, we have a weighted average of that, and that's really what this comes down to, because we can have unequal sample sizes when we have two groups. Here we had just one group, okay, and we were comparing it to a parametric mean. The other thing that's different is in this numerator we have mu1 minus mu2. And in fact, one might postulate whether, you might ask whether the difference between two sample means is greater than some difference between two parametric means, but typically we are assuming that this equals 0, or we're testing. Our null hypothesis is that mu1 equals mu2, in other words, mu1 minus mu2 equals 0, right? Because those are equivalent expressions. Okay, so TS is the student's t-value you get when you're comparing two sample means. So let's take a look at what that might look like. So not very nice axes there, but I'm going to go ahead with it. So we have y1 bar here. Oh, there's my white-throated sparrow. And then we have y bar 2. Thank you, clock. This is why I haven't been doing these in my office, because I have a white-throated sparrow in my office. Anyway, we're asking what is the probability that I could get y1 and y2 bar being that different, you know, this far apart, when in fact they were drawn from a parametric population with the same mean. mu1 equals mu2. Okay, so that's really what we're asking, is what is the probability that we could get these means and standard errors, given the standard errors, the variances. What is the probability I could get distributions that are that far apart? And so I get a p-value associated with that, and I get a t-statistic that provides me that p-value. So I didn't dwell on this last time, but you know, it's really kind of critical to it is that you understand how to interpret a t-value. So we're going to get a particular t-value. So let's imagine that we, oh, by the way, it's very important that we know the degrees of freedom associated with this. When we have two samples, we could have unequal sample sizes. And so the degrees of freedom is n1 plus n2 minus 2. Okay, so our student's t, you know, let's say that we get a particular value. I have an n1 of, I don't know, 10, an n2 of, let's say 8, and therefore my degrees of freedom is what? 10 plus 8 minus 1 minus 2. So it's going to be 18 minus 2, or 16 degrees of freedom. Let's say I got a t, I performed this t-test, I've gotten my difference between means, I've gotten these sample variances, and I've applied this formula, and I've calculated t equals 3.136. Okay? What do I do with that? How do I know whether my means are significantly different? Well, I need a t-table. So I brought up a t-table here. Let's see if I can show it to you. Okay, so we have a t-table, and so what did I say it was? 3.1. 3.136. Okay, we're gonna 3.136. All right, so typically what I would do is start out by looking at the column that contains a two-tailed test with an alpha level of 0.05. Okay, you all know what alpha levels are now, and you know that this is sort of a threshold by which we're going to judge many p-values, many statistics. So let's take a look at this column. And we're going to go down to our 16 degrees of freedom. So that's the first one here in blue. And we find a t-value of 2.12. Now, clearly, our value of 3.13 is greater than that, which means that it is the difference between the means. If you think of the formula, the difference between the means is greater than might be expected with a 0.05 probability. So we can actually go over to the next column and look at 0.02 probability. It's 2.583. We're still greater than that. In fact, our p-value is greater than this one here, which corresponds to a p-value of 0.01. So we can go all the way over to here, and it's not greater than this one, 0.002. So what can we say? We can say that the p-value is less than 0.01. Now, that is actually for what we're calling a two-tailed test. And I wanted to point out, you know, there are two-tailed tests, and there's, there we go, two-tailed tests, and there are one-tailed tests. And so that's an important thing to consider. So what do we mean by these two-tailed tests and one-tailed tests? Well, it all depends on what our alternative hypothesis is. So our null hypothesis is that mu1 equals mu2, right? But we also want to specify, in this case, an alternative hypothesis. In this case, the alternative might be, for example, that mu1 is actually greater than mu2. In which case, we really only need to look at one tail of the distribution of the t statistic, right? We don't have to test whether it's different, that is, whether it's either greater or less than. What we have to test is only whether it's greater than. So that means we're only going to look at the probability under half of, in other words, we're going to have alpha over 2 as our probability, our cutoff. And so, for example, if we wanted a one-tailed test where we would have alpha equals 0.05 for the one-tailed test, we would look at the two-tailed alpha equals 0.1, right? Because we only need to have it different on one side. So SAS Jump is nice. It gives you actually both outputs when you do a t-test. It gives you a one-tailed and a two-tailed test. But in general, you can just look at this table and you can see that the 0.025, well, the 0.05 one-tailed test is equivalent to the 0.1 two-tailed test. So in other words, it's actually easier to find a difference when you're looking for a particular direction of the difference, which makes sense, right? I mean, it makes sense that if you're only looking at not whether there's a difference, but whether there's one mean is greater than the other, that you only have to compare, you only have to look at one tail of the distribution. At any rate, I just wanted to show you that because that is one thing that can be useful about a t-test. You know, it's less often even thought about with an ANOVA. Generally, you're asking the null hypothesis, is there a difference or not among means? But you don't generally do one-tailed tests in an ANOVA. But with a t-test, you can do a one-tailed test, which gives you a little more power to detect differences when, in fact, your alternative hypothesis is directional. And it can be either direction. You could have mu2 greater than mu1, right? That could be the other alternative hypothesis that you could have, and you can look at it in either way. Now, the one important thing I want to mention is that it's very important that you specify the alternative beforehand, before you carry out the test. And the reason for that is that you corrupt your significance when you look at all three t-values and then pick out the one you like, right? You need to specify what your null hypothesis is and your alternative hypothesis before you perform the test, before your brain knows what it is, because it's unfair to ex post facto go back and say, oh, well, I really wanted to know whether it was greater, not whether it was just different. And it means something because if you are just interested in whether mu1 is greater than mu2, not whether it's less, you then have more statistical power to actually find those differences. It's easier to find those differences. And so it's not fair to change your question halfway through because you corrupt your significance. Okay, so that's the t-test. That's as far as I'm going to go with it. Again, we won't use it much in this class, or you probably won't use it much in the actual biological research that you do. But I think you'll find that it's useful to know it. In fact, particularly reading some of the older literature, you're going to see t-tests a lot, and it's still sometimes usefully used. Okay, that's it, everybody. Have a good one.